All right, the concept of a multiset. In mathematics, a multiset or a bag is a generalization of the concept of a set, unlike a set, allows multiple instances of a multiset's elements. For example, AAB and AB are different multisets, although they are the same set. However, order does not matter, so AAB and ABA are the same multiset. But what does this mean? In a set, we cannot have repeated elements, right? But in a multiset or a bag, we can have repeated elements. So that's the difference between a set and a multiset. Okay, so now let's have a look at what is called a full permutations of a multiset. Okay, I'll give you a concrete example to illustrate this concept. Okay, suppose we have a multiset here, which is a container that contains three red identical tiles and two identical green tiles and two identical blue tiles. And the question is, if I draw 7 elements from the above multiset, how many possible arrangements are there? Okay, I'll give you 5 minutes to think about this question. All right, any ideas? How do we approach this problem? Okay, so we can think of this problem like this. So if all the elements are different with each other, what is the full permutations on this multiset, on this set? If all of the elements are different, the full permutations is 7 factorial, right? And to conduct a full permutations on this set, we can treat it like several steps. First step is to assuming that the 3 red blocks are identical, right? And at the meantime, the 2 green blocks are identical and the 2 blue blocks are identical. So first of all, we need the number of full permutations on this multiset. So suppose this number is x, and x is actually the number we want, right? So this is the first step. After the first step, the next step is to arrange full permutations on these red blocks, right? So how many ways we can do a full permutations on these 3 elements? Number is 3 factorial, right? Next step is to arrange a full permutations on the 2 green blocks. So that means we have 2 factorial number of ways to do this. And similarly, for the 2 blue identical blocks, we have 2 factorial number of ways to do a full permutation, right? So 7 factorial equals x times 3 factorial times 2 factorial times 2 factorial. So that means we can solve our x, right? X is 7 factorial over 3 factorial times 2 factorial times 2 factorial. This is the number of ways of the full permutations on this multiset. Okay, any questions? Okay, so let's make summary. If we have a multiset of 3 red identical blocks and 2 green identical blocks and 2 blue identical blocks, the total number of full permutations on this multiset is 7 factorial over over 3 factorial times 2 factorial times 2 factorial. Note that 7 is total number of elements in this container, and 3 is the total number of identical. 3 to 2 are the number of identical elements of the red blocks, green blocks, and blue blocks, respectively. Okay, so let's generalize this concept a little further. So suppose if we have a container that contains M1 number of identical blue blocks and M2 number of identical green blocks and M3 number of red blocks. The question is, if I draw elements from the above multiset, how many different arrangements are there? Okay. Actually, the method to solve this is similar to what we have used in previous example, right? So we can directly say the total number of permutations is n factorial if we consider all the elements as different, as distinct, right? And because some of them are identical, so we need to divide this number with m1 factorial times m2 factorial times m3 factorial, right? Why? Because for the M1 identical elements, if we do not divide this number, that means we have enlarged the number we want to M1 factorial times, right? So M1 factorial times of the permutations are the same because the M1 number of blue blocks are identical, right? So no matter how you arrange these identical blocks, their corresponding permutations are the same. So we need to divide this number. Okay, any questions? All right, let's make summary. All right, suppose you have a multiset that contains M1 identical tiles, M2 identical elements, and M3 identical elements, and you want to draw n elements from the above multiset and see how many different arrangements are there. The result is n factorial divided by m1 factorial, m2 factorial, and m3 factorial. That's the total number of elements, n factorial, divided by the number of identical elements factorial. Okay? Please write this formula down, and we're going to use it to solve some example questions later. Okay, any questions? No? Okay, let's see an example. How many different letter arrangements can be formed from the letters P, E, P, P, E, R? Okay, so apparently in the letter P, 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 E, R, in this word, all the P's are identical, right? And there are two identical letter E and one letter R. So how many different letter arrangements can be formed from these letters? Okay. So this is actually a full permutation on 1, 2, 3, 4, 5, 6, on 6 elements, right? And there are some identical elements in the container, right? So how do we write the total number of arrangements there? Note that, okay, we can draw a diagram to illustrate this. We have 3 identical P's and 2 identical E's and 1 identical R's. And we want to pick 6 elements and line them up and find number of arrangements, right? So this is a full permutations on a multiset problem. So remember, the model is 6 factorial over 3 factorial times 2 factorial times 1 factorial, right? So what is the final result? Final result is, okay, let's calculate this. 654 times 3 factorial and 3 factorial times 2 times 1. 3 factorial can be cancelled and 2 can be cancelled is a 4. So the final result is 60. So that means we have 60 different ways to arrange these letters. Okay, any questions? No? All right, let's see the next one. In the chess tournament, we have 10 competitors, of which 4 are Russian, 3 are from United States, 2 are from Great Britain, and 1 is from Brazil. If the tournament result lists just the nationality of the players in the order in which they placed, how many outcomes are possible? Okay, this time I'll leave this question for you to solve. I'll give you 5 minutes to solve this question. Okay, have we finished? What is the result? According to the concept we have learned, we can directly write the result as 10 factorial, which is the total number of elements, right? 10, 4 plus 3 plus 2 plus 1 is 10. So 10 factorial divided by 4 factorial, 3 factorial, 2 factorial, and 1 factorial. And final result is 12600. Okay, have we get this correct? Okay, any questions? No? All right, let's see the next one. Next one, how many different signals, each consisting of 9 flags hung in a line, can be made from a set of 4 white flags, 3 red flags, and 2 blue flags, if all flags of the same color are identical? So this means how many different arrangements, if we use these flags and line them in a line, right? How many different arrangements of these elements? Okay, and what's the total number of elements here? 4 plus 3 plus 2, which is 9, right? So according to the formula of the third model of permutations, the numerator is 9 factorial, right? And what is the denominator? Denominator is a product of all these numbers. So 4 factorial times 3 factorial times 2 factorial. This is the total number of permutations on this multiset, right? Okay, any questions? No? Okay, let's see the next one. The child has 12 blocks, of which 6 are black, 4 are red, 1 is white, and 1 is blue. If the child puts the blocks in a line, how many different arrangements are possible? Okay, so assuming that the 6 black blocks are identical and 4 red blocks are identical, how many arrangements are there? I'll give you 1 minute to think about this question. Okay, have you finished? How do we write the result? 12 factorial over 6 factorial, 4 factorial, 1 factorial, and 1 factorial, right? So final result is 27720. Okay, any questions? No? All right, we can take 10 minutes break, and after that, we'll see some questions regarding the probability using permutations. So let's take 10 minutes break. Okay, welcome back, and let's continue our lesson. Next, we're going to have a look at probabilities using permutations. Remember that the reason why we learn the counting techniques is to find the number of sample points in the sample space and the number of sample points in an event. And then we can use a ratio between these two numbers to find the probability of any event, right? Okay, so let's have a look at some examples. First, a 4-digit pin is selected. What is the probability that there are no repeated digits? Okay, what does this mean? This means suppose we have a 4-digit pin, for example, 2013. This is a pin, right? And we choose some numbers to be the pin. What is the probability that there are no repeated digits? What does repeated digits mean? Repeated digits mean, for example, 1, 1, 3, 4. The two ones here are repeated digits, right? So if we select the 4-digit pin, can you find the probability that there are no repeated digits? Okay, so how do you approach this problem? First, we need to consider the sample space, right? Suppose we denote the no repeated digits as an event A. Here we want to find the probability of this event, right? The probability of this event is the number of sample points in this event over the number of sample points in the sample space, right? Okay, so first of all, let's consider the denominator. What is a sample space? How many sample points are there in the sample space? So if we choose 4 digits out of 10, 0 to 9 are 10 numbers, right? 10 digits. So if we randomly choose 4 digits out of 10, how many choices do we have? We have 10 digits and we choose 4. And for each peak, we replace the container with the same digits, right? That means in the sample space, of course, we can have repeated digits. So the number of sample points in the sample space is 10 to the 4th power, right? Okay, so this is the denominator. Now let's consider sample points in the sample space. Okay, so this event, in this event, if we choose 4 out of the 10 different digits, and the requirement is we cannot have repeated digits, right? So that means for each pick, after you pick and you line them up, we cannot replace a container with the same digits, right? This is a permutations without replacement. So how many choices do we have? The number of choices is to pick 4 out of 10. So the result is P 10, 4, right? Okay, so now what is the probability of this event? The probability of this event is the number of sample points in this event, which is P 10, 4, over the number of sample points in the sample space, which is 4 to the 4th power. So this is 5040 over 10,000, which is 0.504, right? This is a probability we're looking for. Okay, any questions? No? Okay, let's see the next example. Next example is a question that raised at the beginning of this chapter, which is a birthday problem. Suppose there are 50 people in a room, complete strangers, randomly chosen. The question is, what is the probability that at least 2 people in this room have the same birthday? So assuming we ignore all the leap years. Okay, I'll give you 5 minutes to think about this question. All right, any ideas? How do you calculate this probability? Okay, so the first question we need to ask is, how many different sample points in the sample space? In the sample space, what is a sample space? Sample space is to pick, so how many different birthday in a year? There are 365 days, right? So there are different 365 different birthdays in a year. The task is to pick 5 birthdays out of the 365 birthdays, right? So in the sample space, we have 365 to the 5th power, this number of different outcomes, right? Because in the sample space, we can't have the same birthday. Task is to pick 50 elements out of the 365 in the container. And after each pick, the element should be put back into the container. So the total number of outcomes is this one. How about in this event? This event requires that at least 2 people in this room have the same birthday. So we can consider the opposite of this event, right? We can use the total number of outcomes subtracted by the number of outcomes in which no people share the same birthday, right? If no people share the same birthday, what does that mean? That means in this container, we will have 365 birthdays. And the task is to pick 50 out of this number. And this time without replacement, right? So if no people share the same birthday, number is P36550, right? So we use total number of methods subtracted by the methods in which there is no shared birthday. That means this number here is total number of cases in which at least 2 people in this room have the same birthday, right? So this is the number of sample points in this event. Okay, so the probability of this event is the total number of sample points in this event divided by the total number of sample points in the sample space, right? So this is our final result. So how do you calculate this? Sometimes we need a calculator, right? So we can go to Google Sheets and open Google Sheets. We can use the formula here to calculate this expression. Okay, the expression is sorry. Okay, first put equality sign. We want to calculate 365 raised to the 50 minus permutations, which is permute 365 50. This is the numerator, right? And also we want to find the denominator, which is 365 raised to the 50. Okay. And now let's calculate the ratio. As you can see here, the probability is 0.97. So the probability of this event is 0.97, which is approximately 97%. That means if you have a room of 50 people, the probability that at least 2 people in this room have the same birthday is pretty high, right? Okay, any questions? No? All right, let's see the next one. Okay, next we're going to do some more practices on the permutations. Okay, so first question, question A, how many different seven place license plates are possible if the first 2 places are for letters and the other 5 for numbers? Okay, so 1, 2, 3, 4, 5, 6, 7. First 3 places are reserved for letters. And next 4 positions are reserved for numbers. Okay, so how many different ways we can complete this task? We can use either the rule of product, right? Because to finish this task, there involves 7 steps. Of course, we can also use permutations, right? So the first step is to arrange the letters, and second step to arrange the numbers. So how many ways can you arrange the letters? For the letters, we have 26 letters, right? And we have 3 positions. That means 26, sorry, for the first 2 positions. So that means 26 squared, right? And the second step is to arrange the numbers. So how many numbers we need? We need 5 numbers, right? And for each step in the numbers, we have 10 choices. So times 10 raised to the 5th power. So this is the total number of arrangements we can have in the in this plate. Okay, B, repeat part A under assumption that no letter or number can be repeated in a single license plate. Okay, so here we have a constraint. For these 2 letters, we cannot have repeated letters, right? So for the first step, how many ways we can finish this task? We can have choose two elements out of the 26 different elements, right? This is the total number of ways we can arrange the letters. So how about for the numbers? Again, this time we cannot have repeated numbers. So that means we must choose 5 out of 10 different numbers without replacement. So this is a number of the second step. And according to rule of product, if we multiply these numbers, we can have the total number of ways we can do for this task, right? So this number is 19656,000, and previous result is 67600,000. Okay, any questions? No? Okay, let's see the next one. Our last example. Okay, I'll leave you 5 minutes. I'll leave you 10 minutes to have a look at this question, okay? And after that, we'll discuss the solutions to each of these. Okay, have you finished? So how do you calculate the first one? In how many ways can 3 boys and 3 girls sit in a row? There's no any constraints, right? So we can treat this problem as 6 people in a line. How many different arrangements for 6 different elements? So the number is 6 factorial, right? This is full permutations on 6 different elements. This number is 720. Next, in how many ways can 3 boys and 3 girls sit in a row if the boys and girls are each to sit together? Okay, this question has a constraint. The boys and girls are each to sit together, right? So we can consider to arrange the boys and then arrange the girls. But first of all, we need to decide which gender is in front. So 2 genders, full permutation on 2 genders is 2 factorial times full permutations on the 3 boys and then full permutations on the 3 girls. So this is the total number of ways we can do this task, which is 72. For the third one, in how many ways if only the boys must sit together? Okay, here we have another constraint. Only the boys must sit together. So that means, first of all, we can treat these 3 boys together as a whole and use this group to do a full permutation, right? So this is a 1, 2, 3, 4, 4 elements do full permutations, which is 4 factorials. And then we can arrange these 3 boys in the group, right? So the second step is to arrange the 3 boys, which is 3 factorial. So the total number of ways is 144. Okay, last, in how many ways if no 2 people of the same sex are allowed to sit together? So we have 6 persons, right? We can consider using the rule of product. So to complete this task, there are 6 steps, right? For the first step, how many choices do we have? We can pick any one from these people, right? So we have 6 choices. So after we have done this, how many choices do we have for the second position? Note that no people of the same sex are allowed to sit together. So for the next position, we have to choose from the opposite sex, right? So that means we only have 3 choices. So after you have arranged the first 2 persons, how about the next one? The next one, you have to choose from the opposite sex, which means we have 2 choices only, right? So following this logic, the next one, we only have 2 choices. And for the next one, we have only 1 choices. For the last position, we have only 1 choices. So total number of choices is 72, okay?